Good morning, everybody. Today we are going to discuss single particle cell model. In the previous semester, we have discussed about cell model. Let us briefly recap the cell model. What is it? Cell model can explain magic numbers and it can predict spin and parity of nucleus. We have only seen that even nuclei and odd even nuclei has been treated in cell model, but in that cell model we did not mention about odd nuclei. In cell model, have assumed that a single odd nuclei outside is responsible for spin of the nucleus. Now, in case of odd nuclei, there are two nucleons, odd nucleons outside. So we cannot predict, according to the old cell model, what will be the spin of the nucleus. Single particle cell model considers this. In this model, it assumes that there are interactions between the nucleons which are outside the cell. That means odd nucleons, they have interaction between them. Now, what is the nature of interaction? It cannot be estimated in detail, but one thing we can say for sure that as these are fermions, anti-symmetrization of the wave function by changing the two particles is applicable, and with this there are some restrictions about the allowed values of total angular momentum J. The spin of even odd and even nuclei are the same with this assumption. So in this model, spin of the odd nuclei will lie between two numbers Jn minus Jp mod, that is difference from larger one to smaller one, to Jn plus Jp, any number in between these two, and Nordheim rule is applicable here. Now what is the Nordheim rule? To understand this, we have to define Nordheim number. What is this? And this is Jn plus Jp minus Ln minus Lp. This is the Nordheim number. Now as you know, J equals to L plus S in LS coupling. S has a value half, plus half or minus half. So accordingly, two cases may arise. In case 1, when say Jn equal to Ln plus half and Jp equal to Lp minus half, or vice versa. That is Jn equal to Ln minus half and Jp equal to Lp plus half. Then if we calculate Nordheim number, then it will be 0. In that case, spin of the nucleus will be I equals to mod Jn minus Jp, which is called strong rule because definite value is obtained. In case 2, where Jn equal to Ln plus half, Jp equal to Lp plus half, or Jn equal to Ln minus half and Jp equal to Lp minus half. In this case, Nordheim number will be equals to either +1 or -1. And here the spin of the nucleus will be determined by any of the two numbers. That is, it may be Jn minus Jp mod or Jn plus Jp. So this is called weak rule. Why it is weak? Because no definite number is obtained between two numbers. Any one can be there. Let us take some example. For example, phosphorus 30. Now it has proton number 15 and neutron number 15. If you use our cell model to distribute the nucleus, you will see that the odd nucleus, that means the odd proton and odd neutron, lie in the 2s hub subcell. So here Jn equals to Jp equal to half and Ln equal to Lp equal to 0. So using Nordheim's number, n equals to +1. So here weak rule will be applicable. So spin of phosphorus 30 would be either 0 or 1. Parity is even because L equal to 0. Observed spin parity is 1 plus. Let us take another example. Potassium 42. Their proton number is 19. Neutron number is 23. Now according to the cell model, the last odd proton lies in the 1d3/2 subcell and last neutron lies in 1f7/2 subcell. So here Jp equals to 3/2, Jn equals to 7/2, Lp equals to 2, Ln equals to 3. We calculate Nordheim number, then it comes out to be 0. So strong rule is applicable here. And using strong rule, we can see that I equal to mod Jn minus Jp equals to 7/2 minus 3/2 equal to 2. Parity is odd. Spin parity 2 minus is observed. Now I am giving you some more examples. You will work it out and give me the result. One is nitrogen 14, then sodium 22, sodium 24, chlorine 36. You calculate it using cell model. What will be its, all these nuclei are odd nuclei. What will be its spin according to Nordheim's rule. Now the predictions of single particle cell model. For even nuclei, as expected, spin is 0. For odd even nuclei, spin is determined by the J values of the last odd nucleon. For odd nuclei, the value of spin is determined by the Nordheim's rule. So, in precise, this is exactly single particle cell model. I think it is fairly simple. Now, we are moving to a more complex problem, which is collective model. Now, what is the intention behind this model? What led us to consider collective model? Cell model of the nucleus has been able to explain many features of nucleus. It can explain magic numbers, it can predict spin parity, it can predict magnetic moment, magnetic dipole moments. But quadruple moment of the nucleus cannot be explained with cell model. That means the prediction by the theory and the experimental value is far apart. Generally, experimentally found quadruple moments are very large. In the figure, you will see the quadruple moments of odd number of nucleons. You clearly see that just before the closed cell, quadruple moment is, the closed cell is denoted by arrow lines. Quadruple moment is tremendously high. Now, to explain this thing, scientists tried many ways. Among them, J. Rainwater in 1950 introduced an idea which we will discuss today. The idea is, while the odd nucleon is moving in central potential, nuclear potential, it will distort or deform the shape of the nucleus. That means if we consider a single odd nucleon which is moving in the fields of other nucleons, which we call core, then due to the motion of the odd nucleon, the core, form of the core will be deformed from spherical shape. And due to this deformation, quadruple moment may arise, because we know for spherical charge distribution, quadruple moment will be 0. Why for spherical charge distribution quadruple moment will be 0? We will discuss it very shortly. But for the time being, we can see that deformation of the nucleus from spherical shape may be the reason behind the observed large electric quadruple moments. Now, in order to calculate the total energy, we have three terms: E total equal to E rotational plus E vibrational plus E nuclear. E nuclear is the energy of the single odd nucleon, and E rotational and E vibrational energy is the energy of the deformed rotational and vibrational energy of the deformed core. Now we have to calculate E rotational and E vibrational energy of the deformed nucleus. Now how to calculate it, we will discuss in the next class. Experimental evidence points that large deformities of the nucleus occur when odd nucleon number is greater. For A in between 145 to 148, and for A greater than 226, the energy difference between the ground state, 0 plus ground state, and 2 plus first excited state is of the order of 100 keV. And near the closed cell, that means near the magic number, the nuclear equilibrium state is nearly spherical. That's why in magic numbers, nuclear quadruple moment is small, but just adjacent to it, or that is just before the closed cell and after the closed cell, the quadruple moment is large. Now, before we may proceed to calculate rotational and vibrational energy of the nucleus, you have to consider quadruple moment first. What is the quadruple moment? As you know, in your undergraduate electrostatics classes, you have heard of expansion of potential. For example, if you consider potential of a charge at point, charge distribution rho r dash, that means charge density is at point r dash, and we are considering potential at a point phi, at a point P, which is at a distance r from the origin. Then the form of the potential would be phi will be 1 by 4 pi epsilon 0 integration over rho function of r dash by r minus r dash the mod and integration over dv dash. Now if we write r dash equals to r1 equals to r minus r dash, then this integration is 1 by 4 pi epsilon 0 integration over rho r dash dv dash by r1. Now the function 1 by r1 can be expanded around 1 by r. That means we are expanding 1 by r distance from source point to the field point in terms of 1 by r inverse of the distance from origin to the field point. Then the expansion will be like this. I'm showing you in my copy the form of the expansion. It is written in tensorial form because we are considering quadruple moments. Here del operator is replaced by del xi, where xi runs from 1 to 3, 1, 2, 3. X1 represents x, x2 represents y, and x3 represents z. I'm showing you the form of expansion. Here it is. You can see that the expansion of 1 by r1 around r is 1 by r1 equals to 1 by r minus summation over I xi dash del xi dash of 1 by r plus half summation over I summation over j xi dash xj dash del 2 del xi dash del xj dash 1 by r plus dot dot. Now if we change the differentiation with respect to unprime coordinates, then we know that del xi dash will be equals to minus del xi. With this substitution, the expansion becomes 1 by r1 equals to 1 by r minus summation over I xi dash del xi of 1 by r plus half summation over I summation over j xi dash xj dash del 2 del xi del xj of 1 by r plus other terms. We have taken only 3 terms. And consequently, if we put this expansion in the expression for potential, then the potential can be written written as phi equals to phi 1 plus phi 2 plus phi 3, where phi 1 is the monopole term, phi 2 is the dipole term, and phi 3 is the quadrupole term. You know, in monopole term, the denominator will be 1 by r and numerator is 1 by 4 pi epsilon 0 integration over rho d v dash. In dipole term, it will be 1 by 4 epsilon 0 integration over summation over I xi dash del del xi of 1 by r rho r dash dv dash. This is the dipole term. You know, in this term, the denominator there will be there will be r square, and in quadruple moment, in denominator there will be 1 by r cube. I am showing you the forms of these three terms: monopole term, dipole term, and quadruple terms. Here it is. First one is monopole term, the second one is dipole term, and the third one is quadruple term. Here in quadruple terms, we have taken the summation sign over the integration, away from the integration, because summation is over the unprimed coordinates and integration is over the prime coordinates. You can see that it is in the tensorial form. Now we know that del square 1 by r equals to 0. If you write this in tensorial form, then it comes out to be summation over I, summation over j, del 2 del xi del xj of 1 by r delta I equals to 0. Here delta I is the Kronecker delta, which has the value 1 if I equal to j and equal to 0 if I not equals to j. And if we multiply this expression with 1 by 24 pi epsilon 0 integration over rho r dash square dv dash, and subtract it from the expression for phi 3. Since we know that this expression is equals to 0, then phi 3 will be unchanged, unaltered. Then the expression for phi 3 becomes like this: 1 by 24 pi epsilon 0 summation over I summation over j del 2 del xi del xj of 1 by r integration over rho r dash in second bracket 3 xi dash xj dash minus r dash square delta ij second bracket close dv. This is the form of the expression. Actually, this is the form of the expression. What we have done, just multiplied the term del square 1 by r equals to 0 with the term and subtracted it from the quadruple moment term. The resultant term will also be quadruple moment, and written the form in this way. From this expression, the quadruple moment, the potential term, quadruple term will be 1 by 24 pi epsilon 0 summation over I summation over j qij del 2 del xi del xj of 1 by r, where qij is the term we call quadruple moment tensor because it has 9 components. Its expression is the integration over rho r dash second bracket 3xi dash xj dash minus r dash square delta ij second bracket close. This qij is called quadruple moment tensor. You can see that in monopole term, if we don't consider the integration or the integration has been performed, then it will be charge 1 by 4 epsilon 0 charged by distance, charged by r. In dipole term, dipole moment by r square. In quadruple term, it will be qij by 1 by r. So this quadruple moment qij is a tensor which has 9 components. So there are 9 unknowns. But fortunately, symmetry makes the problem very simple. From the expression, we can see that qij is symmetry. That is, if we interchange the indices I and j, then it will be same. That is qji equals to qij. So out of 9 components, 3 components has been reduced. That means the out of 6 of diagonal terms, 3 are only independent and rest 3 are dependent on them. So number of variables now reduces to 6. However, if we take the axis to be principal axis, then you know the off diagonal terms vanishes. So there remains 3 independent quantities. Only the diagonal terms remains, off diagonal terms vanishes. Further, we can investigate that trace of the matrix is the sum of the diagonals. If we perform summation over j qjj, then you see that it comes out to be 0. So sum of the diagonal terms, that means q11 plus q22 plus q33 equals to 0. So there are only 3 variables, only 2 independent quantities because there is a relation between 3 variables. So one variable is reduced. Finally, if the charge distribution is axially symmetric, that is, if it is roulette or oblate, then q11 and q22 are same. So we are left with only one independent component, which is q33, and whose expression is integration over rho r dash first bracket 3z dash square minus r dash square dv dash equals to q0. So you see that quadruple moment, in considering the quadruple moment, only we have to consider q3 theta, not the others, provided we take the nucleus to be roulette or oblate sphere. That is, if the nucleus is deformed from spherical shape, but it retains its symmetry, then the calculation of quadruple moment term is simple, and we have to consider only the one term out of 9 components of quadruple moment term tensor. Next, we will consider the rotational and vibrational motion in the next class. today this much is enough. I will suggest you to go through the notes that I have provided in the WhatsApp group. I think it is fairly simple and the calculations are very easy, but I will suggest you to do the calculation on your own, so things will be very clear to you. Thank you.